Pluto, a distant and perplexing smaller Earth, was once a separate member of our family of planets in the solar system. However, subsequent alarming statements made by Neil deGrasse Tyson, a prominent astrophysicist, brought Pluto back into the spotlight, alongside Michio Kaku. With a stunning entrance into public discourse, they claimed that this frosty world might be on a crash course with Neptune. But how could this occur, and what might happen as a result? Are we witnessing a fascinating cosmic phenomenon, or is there another aspect to this looming infinite crash? Join us as we explore the matter and the potential outcomes of a Pluto-Neptune collision. Pluto, a former planet that was reclassified as a dwarf planet in part due to its baffling orbit, continues to be a topic of interest and research in the cosmic community. According to recent forecasts from leading researchers studying Pluto's trajectory, it is dangerously close to Neptune's orbit. Neil deGrasse Tyson and astrophysicists Michio Kaku and others are sounding the alarm about a potentially dangerous collision between these two worlds, an event that could pose an enormous threat to Earth. But how could such an event happen? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit. Since its discovery in 1930, Pluto has only completed one full revolution. What makes Pluto's orbit so unique? Unlike the nearly circular orbits of the major planets, Pluto's path is highly elliptical and inclined at an angle of 17 degrees from the ecliptic plane. This extreme inclination makes Pluto's orbit significantly steeper than the other planets. Another fascinating aspect of Pluto's orbit is its synchronization with Neptune's. For approximately 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, defying expectations based on their positions in the solar system. This raises an obvious question: why haven't Pluto and Neptune collided? The answer lies in gravity and the complex influences of celestial mechanics. Shortly after Pluto's discovery, astronomers struggled to understand its unusual path, which deviated significantly from the relatively flat plane of the solar system. Pluto's steep inclination and eccentricity only deepened the mystery. Eventually, astronomers realized that Pluto's orbit intersects Neptune's, yet remains stable due to a gravitational phenomenon known as orbital resonance. The intricate mechanics of celestial bodies play a crucial role in preventing a collision. The three-body problem in space concerns how three celestial objects, such as Pluto, Neptune, and the Sun, move and influence one another through gravity. Predicting their precise movements is incredibly complex. In Pluto's case, its path is stabilized through a delicate gravitational interplay with Neptune. Key factors contributing to Pluto's stable orbit include 1. Orbital resonance. Pluto and Neptune follow a 2:3 resonance, meaning that for every 2 orbits Pluto completes, Neptune completes 3. This resonance ensures that Pluto is always positioned at least 90 degrees away from Neptune when their orbits cross, preventing a collision. 2. Scope calibration. This refers to the vertical movement of celestial bodies. Because Pluto's orbit is highly inclined, even when it comes closest to Neptune, it is positioned much higher than Neptune's orbital plane, adding another layer of protection. 3. VZK oscillation. Named after scientists who studied it, this oscillation describes how Pluto's movement is influenced by the gravitational pull of both Neptune and the Sun. Despite apparent disorder, this oscillation helps maintain Pluto's stable orbit over extremely long timescales. These combined factors ensure that Pluto does not collide with Neptune or stray unpredictably. The three-body problem helps us understand the complexities of these orbits, as gravitational interactions constantly shape celestial mechanics. In the late 1980s, simulations revealed that despite these stabilizing mechanisms, Pluto's orbit is chaotic in the long term. Small variations in initial conditions can lead to significant deviations over millions of years. However, Pluto's orbital properties have been found to remain stable over extremely long time scales, likely billions of years, thanks to the influence of other massive planets like Jupiter and Saturn. Jupiter's gravity, in particular, plays a major role in keeping Pluto's orbit consistent. Saturn also contributes to this delicate balance. These planetary interactions work together to ensure that Pluto remains safely on its course. Without these stabilizing influences, Pluto might have been ejected from the solar system or sent on a collision course with another planet. The study of Pluto's orbit is crucial to understanding the broader mechanics of our solar system. It highlights how even seemingly unstable orbits can reach a state of equilibrium through complex gravitational interactions. Moreover, it underscores the importance of continuous observation and research to deepen our understanding of the universe. Delving into the depths of space forces us to confront the unpredictability of celestial mechanics. Pluto's orbit exemplifies orbital chaos, a term used to describe the sensitive dependence of an orbit on its initial conditions. Even minor changes in Pluto's speed or position can significantly alter its long-term trajectory. Virtual simulations have been invaluable in studying Pluto's movements. Using intricate mathematical models, astronomers can simulate how Pluto interacts with other celestial bodies. These studies reveal how even small gravitational tugs can result in major shifts over time. Simulations conducted in the late 1980s provided a fascinating insight. Despite stabilizing factors like orbital resonance, Pluto's orbit is still subject to long-term unpredictability. Tiny changes in its position or velocity can dramatically alter its future path. However, despite this chaos, Pluto's orbit has remained stable for billions of years. In conclusion, while Pluto's orbit appears erratic, underlying forces maintain its stability over vast timescales. This balance between chaos and order is a defining feature of celestial mechanics. Understanding Pluto's orbit not only sheds light on the dynamics of our solar system but also reminds us of the immense complexity of the universe. Despite all our advancements, Pluto continues to challenge our understanding, proving that there is still much to learn about the cosmos. The long-term fate of Pluto's orbit. While current simulations suggest that Pluto's orbit remains stable for billions of years, there is still some uncertainty about its long-term trajectory. The interactions between Pluto and other planets, especially Neptune, Jupiter, and Saturn, play a crucial role in shaping its path. Over time, gravitational perturbations could gradually alter its orbit, leading to potential changes in its relationship with Neptune. One possibility is that Pluto's eccentricity and inclination could slowly shift due to the cumulative gravitational influences of the giant planets. While the 2:3 resonance with Neptune currently protects Pluto from collision, even minor disruptions could eventually weaken this resonance. If this happens, Pluto's orbit could become increasingly chaotic, raising the possibility, though still highly unlikely, of a destabilizing event in the far future. Could Pluto be ejected from the solar system? One of the most dramatic possibilities is that Pluto could be ejected from the solar system entirely. Gravitational interactions with massive planets, particularly Jupiter and Neptune, could one day send Pluto into an unstable trajectory. If Pluto were to cross paths with a large enough perturbation, such as a passing star or an undiscovered massive object in the outer solar system, its orbit could be thrown into disarray. Simulations of planetary migration suggest that in extreme scenarios, objects like Pluto could be flung into interstellar space, becoming rogue planets or icy bodies drifting between stars. However, such an event is highly unlikely in the near future. Pluto's current stability suggests that it will remain part of our solar system for billions of years. The influence of the Kuiper Belt. Pluto is not alone in its distant region of the solar system. It is part of the Kuiper Belt, a vast region of icy bodies beyond Neptune. These objects, sometimes called trans-Neptunian objects, TNOs, share similarities with Pluto and provide valuable insights into the history of our solar system. The Kuiper Belt is home to a variety of small planets and icy bodies, some of which follow highly eccentric and inclined orbits similar to Pluto's. Notable objects like Eris, Haumea, and Makemake are considered dwarf planets, much like Pluto. The gravitational interactions between these Kuiper Belt objects and the giant planets could also influence Pluto's orbit over time. If Pluto were to interact with another massive Kuiper Belt object in the future, its trajectory could shift in unpredictable ways. Could Neptune and Pluto ever truly collide? Despite Pluto's orbit crossing Neptune's, a direct collision is nearly impossible due to the protective effects of their orbital resonance. However, if an external force, such as a rogue planet, a passing star, or even a major shift in Neptune's own orbit, were to disrupt this delicate balance, the risk of a close encounter could increase. Astronomers rely on long-term simulations to study such possibilities, but as of now, all evidence suggests that Pluto and Neptune will continue their cosmic dance without colliding for the foreseeable future. What Pluto teaches us about the nature of orbits. Pluto's orbit is a perfect example of how celestial mechanics can be both stable and chaotic at the same time. The gravitational interactions that keep Pluto in check demonstrate the delicate balance that governs the motion of planets and smaller bodies in our solar system. This understanding is not just important for Pluto, it applies to countless other objects, from asteroids to exoplanets orbiting distant stars. The study of orbital chaos helps astronomers predict the movement of potentially hazardous asteroids, understand the formation of planetary systems, and even explore the possibility of life on exoplanets with unusual orbits. The future of Pluto exploration. While Pluto was long considered a mysterious and distant world, our understanding of it changed dramatically with NASA's New Horizons mission in 2015. This spacecraft provided the first detailed images and data from Pluto, revealing stunning geological features such as vast ice plains, towering mountains, and a dynamic atmosphere. Future missions to Pluto and the Kuiper Belt could provide even more insights into its orbit and the history of the outer solar system. There are proposals for orbiters or landers that could study Pluto in greater detail, potentially unlocking even more secrets about its interactions with Neptune and the broader solar system. Conclusion. Pluto's orbit is one of the most fascinating and complex in our solar system. While it appears chaotic, it is governed by intricate gravitational interactions that keep it stable over long time scales. The relationship between Pluto, Neptune, and the giant planets highlights the delicate balance that shapes planetary systems. Even though Pluto's long-term fate remains uncertain, current studies indicate that it will continue its cosmic journey for billions of years. Whether it remains a stable member of our solar system or faces future disruptions, Pluto serves as a reminder of the dynamic and ever-evolving nature of the universe. As our understanding of planetary orbits improves, Pluto will remain a key subject of study, offering valuable lessons about celestial mechanics, the formation of planetary systems, and the potential for future exploration beyond Neptune. Beneficial insights into the solar system's broader dynamic system demonstrate how the position of each planet can have vast effects on stability and the trajectories of other bodies. Why do they stand out in the system? Astronomers are just now raising concerns regarding a possible collision. Despite all of this, Pluto and Neptune are influenced by complex forces attempting to prevent such a situation from occurring. Famous astrophysicist Neil deGrasse Tyson provides unique insight into the mysteries of our solar system, specifically the captivating case of Pluto. Tyson is known for his role in reclassifying Pluto from a planet to a dwarf planet. His analysis sheds light on the evolving understanding of celestial mechanics and the public's fascination with the unknown reaches of space. Tyson's stance on Pluto's reclassification is rooted in the broader understanding of the solar system. He does not view the new classification as a bad thing but rather as an essential modification in our growing knowledge of celestial bodies. His approach to studying the Sun's orbit and the science of celestial mechanics underscores his perspective that learning and adaptation are crucial to understanding the complexities of Pluto's orbit. In addition to its interactions with Neptune, Pluto's orbit has remained stable for a long time, but it may undergo significant changes in the future. This possibility serves as a reminder of how much remains to be learned about the forces that shape the solar system. The study of Pluto's orbit provides a fascinating investigation into the intricate gravitational interactions within the solar system. While Pluto's current path appears stable, relationships between Pluto and Neptune suggest that even seemingly stable orbits can shift over time. Neil deGrasse Tyson and other astrophysicists continue to explore the mysteries of the universe, helping us better understand the delicate equilibrium that governs celestial movements. While a collision between Pluto and Neptune is not imminent, their dynamic relationship highlights the unpredictability of the cosmos. Scientific theories about Pluto's orbit must take into account the broader implications for our understanding of the solar system and the vast universe. Pluto's journey serves as both an interesting case study and a reminder that many hidden complexities remain to be explored. One essential concept in this discussion is orbital resonance, particularly the 2:3 resonance between Pluto and Neptune. This means that for every 2 orbits Pluto completes around the Sun, Neptune completes 3. Despite the fact that their orbits cross, this resonance prevents them from colliding. Gravitational interactions ensure the stability of their paths, working together to prevent a catastrophic collision. The significance of resonance in cosmic stability cannot be overstated. It illustrates how celestial systems, even in their chaotic gravitational interactions, can regulate themselves over time. Understanding this resonance helps explain why Pluto, despite its eccentric orbit, has remained stable for billions of years. Larger planets like Jupiter, Saturn, and even Uranus play crucial roles in maintaining the stability of smaller bodies' orbits, including Pluto's. Jupiter's immense gravitational force acts as a kind of shield, influencing the inner solar system and deflecting asteroids and other dwarf planets. Some researchers believe that Jupiter's gravity may have prevented Pluto from being ejected from the solar system entirely. Without this protective influence, Pluto's orbit could have been far more unstable. Furthermore, gravitational perturbations continue to influence planetary and dwarf planet orbits over long periods. Even though Pluto's orbit appears relatively secure at the moment, the positions of Neptune and other massive planets can cause gradual shifts. These disturbances are part of a larger mechanism that shapes orbital dynamics. Astronomers have used sophisticated simulations to track the solar system's movements and predict how Pluto's orbit may evolve in the future. These models allow scientists to explore different scenarios, considering gravitational interactions and initial orbital conditions. Another crucial factor in understanding Pluto's behavior is the role of observational technology. The study of distant objects like Pluto has only been possible thanks to advances in telescopic technology. The New Horizons mission in 2015 provided humanity with new data about Pluto, including atmospheric features, surface conditions, and interactions with solar wind. This information has significantly improved our understanding of Pluto's orbit and its potential future movements. As telescopes continue to advance and more missions are launched to the outer reaches of the solar system, our knowledge of these distant bodies will continue to expand. This growing body of knowledge may one day allow scientists to make even more precise predictions about Pluto's future and its interactions with Neptune. Additionally, Pluto's orbit offers valuable insights into the early history of the solar system. The highly eccentric orbits of Kuiper belt objects, including Pluto, can be linked to planetary migration processes that occurred billions of years ago. During this period, massive planets, particularly Jupiter and Saturn, shifted their orbits, disrupting smaller objects in the solar system. This process may have contributed to the current configuration of the Kuiper belt and Pluto's unusual path. By studying Pluto's interactions with Neptune, scientists can gain a deeper understanding of the solar system's early dynamics and how it evolved into its present state. Looking ahead, the possibility of future disruptions to Pluto's orbit remains an intriguing subject of study. While Pluto's current stability is well documented, it is important to remember that the solar system is a constantly changing environment. Objects from the Oort cloud, gravitational shifts among gas giants, or unforeseen celestial events could potentially alter Pluto's trajectory in the distant future. Despite the low likelihood of a collision between Pluto and Neptune, unexpected gravitational interactions could still occur. These possibilities highlight that Pluto's significance extends beyond its classification. It serves as a key to understanding the broader processes that govern the movement of celestial bodies across our solar system. The future of Pluto's orbital evolution. While Pluto's current trajectory remains stable due to its resonance with Neptune, long-term studies suggest that subtle gravitational influences could lead to gradual variations over millions or even billions of years. These shifts may alter its eccentricity, inclination, or perihelion, the point at which it comes closest to the Sun. Scientists are particularly interested in how Pluto's orbit might change due to cumulative perturbations from other planets, including Jupiter and Saturn. One possible scenario is that Pluto could experience slight orbital drift, leading to variations in its resonance with Neptune. While this would not necessarily result in a collision, it could cause shifts in its position relative to other Kuiper belt objects. Over extremely long timescales, changes in planetary alignments might influence Pluto's orbit in ways that astronomers are still trying to predict. The role of the Kuiper belt and beyond. Pluto is just one of thousands of objects within the Kuiper belt, a vast region of icy bodies beyond Neptune. Many of these objects, sometimes referred to as trans-Neptunian objects, TNOs, share characteristics with Pluto, such as eccentric orbits and interactions with Neptune's gravitational field. Studying Pluto helps scientists understand the larger structure of the Kuiper belt and how it might have formed. There is also growing interest in exploring the scattered disk, a region of the solar system where objects have highly elongated orbits, possibly due to past encounters with Neptune. Some astronomers suspect that interactions between Pluto and these distant objects could provide clues about how the early solar system evolved and whether similar processes are occurring in exoplanetary systems around other stars. The search for Planet 9. One of the most intriguing theories in planetary science today is the possible existence of a yet undiscovered ninth planet, often referred to as Planet 9 or Planet X. This hypothetical planet, believed to be several times the mass of Earth, could be lurking in the outer solar system, influencing the orbits of distant objects, including Pluto. If such a planet exists, it might exert gravitational forces that subtly alter Pluto's orbit over millions of years. Researchers continue to study anomalies in the orbits of Kuiper belt objects to determine whether they can be explained by the influence of an unseen massive body. If Planet 9 is eventually discovered, it could reshape our understanding of Pluto's place in the solar system and its long-term orbital evolution. The impact of future space missions. Upcoming space missions could revolutionize what we know about Pluto and the outer solar system. While New Horizons provided humanity's first close-up images of Pluto, future missions could include orbiters, landers, or even sample return missions. For instance, proposals for spacecraft designed to study the Kuiper belt in greater detail could offer insights into how Pluto interacts with its environment. Advanced telescopes, both in space and on Earth, will continue tracking Pluto's orbit with increasing precision, helping refine predictions about its long-term stability. Pluto as a window into the solar system's history. Pluto's story is far from over. Beyond its classification as a dwarf planet, Pluto serves as a dynamic and evolving world, providing critical clues about planetary migration, resonance mechanisms, and the forces shaping our solar system. By studying Pluto and its interactions with Neptune, astronomers gain a better understanding of the delicate gravitational balances that govern celestial mechanics. This knowledge extends beyond Pluto, offering a glimpse into the early solar system and helping us predict the fates of other distant objects. Ultimately, Pluto remains a fascinating subject, not only because of its own mysteries but also because of the broader questions it raises about planetary science, orbital mechanics, and the ever-changing nature of the cosmos.